just as for the collocation method, we can plot all of this. If I want to plot the harmonic data coming from the time domain simulation over with the Fourier analysis over the last fundamental period, then I can do this. And naturally, I can also have a look at the waveforms. If I want to look just at the last fundamental period, I can run on this one. But I would like to see the complete time span, so I can display among the time domain sources the one that covers the complete time span. I do Control-Enter as usual, and I obtain these files, these waveforms. Naturally, they're quite oscillatory because I have initialized the simulation from 0, except for the input, which is indeed the waveform with a constant component and a fundamental frequency component as defined. For simplicity, I can again have a look at all the waveforms together. Here they are. So in this particular simulation, I see that the system has not reached a steady state. So to reach a steady state, I can do a few things. I can solve for longer, let's say 15 seconds. Let's have a look at that. It will take a little bit longer to solve. That's about 15 seconds. Naturally, all of this depends on the number of equations, the number of variables, the stiffness of the system, on the solver you use, on the tolerance you use, and on the computer you have. The solver is done. We can again have a look at the waveforms. Here they are, and we see that if we leave enough time, then the system reaches, arrives closer to a steady state. There is something you could do as well, is instead of restarting from the very beginning to gain some time, you could ask to start not from 0, but from the solution. We'll still solve for 5 more seconds. Here it doesn't matter. I could indicate 15 and ask to go up to 20, but really it doesn't matter. I can just rerun over a vector that I define as starting from 0. So let me close some figures and plot the most recent one. So it has restarted from the last solved point, and it has converged even more to steady state. This is perhaps something we can see with this. Yes, so there is still a little transient. In any case, what I would like to do now is check whether the results of the collocation method match the steady state waveforms provided by the time domain simulation. That is something that I can do by just plotting both at the same time. Naturally, to give them a difference, I give them a different style. So, not so surprisingly, the results of the collocation method span only one fundamental period, while those of the time domain simulation span 5 seconds. I would like to check only the last fundamental period, so instead of plotting the complete time span, I plot only the last fundamental period. And this time, the two results indeed match properly. This is maybe something we can see even better by giving a different style. Let's say that the collocation, the waveforms related to the collocation method will have circles. Here it's unreadable because the sampling frequency is too high. You can reduce the number of points by saying I would like to show only 1 point out of 100. And this is what we have. So the points are indeed very close to the results of the time domain simulation. There is still some difference because the time domain simulation had not converged exactly to a steady state, but if we give it even longer, it will converge to the results provided by the collocation method. If you want to do some disturbance, let's say you would like to add from a given step time, which I will now define to be, let's say, 2 seconds. After 2 seconds, it will also include an additional disturbance, which is of amplitude 0.05 times Vs. So since Vs is equal to 1, it is 0.05, and at the fifth harmonic frequency. In general, when you use steps, you have to make sure to use a mask so that you only modify the values of the input, but after the time of the mask, after the time of the step. If we do this, let's restart the time domain simulation. I will start from the source. So I will use the results of the collocation method to describe a periodic trajectory, and I will say that the initial point should be on this particular trajectory. This means that the time domain simulation will start directly in steady state, but also after 2 seconds, it will start to have an additional disturbance. So this is something we can see by running the simulation. It is done. I go to the plot and I will have a look at the complete time span that I just solved. Let me rerun with just a normal line. Okay, so we see that indeed the simulation starts directly in steady state, and after 2 seconds there is a disturbance on the source voltage, which is in yellow. Naturally, the capacitor voltage and the inductor current react as well. But I see that this creates a transient which does not reach steady state. So for it to reach steady state, I will make the simulation last longer. I go back to the main and I say, I would like to start from the last point, so the solution, and I will simulate for, let's say, 15 seconds. So the simulation is done. I can plot it and I observe this. At the time, at the start point, it was still a transient, but we see that slowly it reaches a steady state. Naturally, it is a steady state with harmonic component. It is essentially a new periodic trajectory. Now, if I would like to compare with the results of the collocation method, I do that on the very last fundamental period. And clearly, they do not match. This is expected because although in the time domain simulation I have included a perturbation at the fifth harmonic, this is a perturbation that was not included in when we last solved the collocation formulation. So to have a perfect match, I would like to also indicate that there is a fifth harmonic component in the spectrum of the source voltage. This is something that I can do by indicating that I would like to define three coefficients at ranks -5 and +5, and it will be a smaller amplitude equal to 0.05 times Vs without phase shift. Okay, and naturally, if I want this to work, I also have to rerun the collocation method with a maximum harmonic rank equal to 5. I run this. I have again the eigenvalues of the frequency lifted system. I see that the solver has converged to within a small error, so I have confidence in the result. I will briefly close all previous plots. And now I can access again the plot here. So naturally, since I have removed quite a few points, it doesn't seem too much properly, but this is something that I can improve by showing more points. And for this purpose, I will have no density reduction, just having dashed lines for the results of the collocation method. And you see they are almost perfect. The small difference that remains comes from the fact that the time domain simulation still there was still some transient on the results of the time domain simulation method, but you see that they are now very close to the steady state periodic trajectory found by the collocation method.